Hello, this is extra practice for quiz 2 in Math 1342, Calculus 2. Quiz 2 covers 2.5, which is improper integrals. We have both type 1 and type 2, and then 2.6, which is numerical integration, Simpson's rule, and trapezoid rule. And you can see my few extra problems here to practice to get ready for this quiz. We begin with 1a. For each improper integral, we will find its exact value or show it diverges. Now, don't forget, fundamentally, every improper integral is first a definite integral and then a limit. And this should be shown in your work. So for this first one, we write the definition. It's a limit as b goes to infinity, the integral from 1 to b. And then I'll rewrite this as a power. 6 times x minus 3 to the minus 2 times dx. This type of function where the inside function has derivative 1, I will just integrate. Technically it's substitution, but du is dx here. And so I will just integrate. Well, we add a power. This would be x plus 3 to the minus 1, and then divide by the higher power. And then we evaluate between 1 and b. I am in the definite integral part. And you notice, I just rewrite this. At the end is when I will calculate the limit. Well, this -1 exponent is really in the denominator. So I have a minus 6, and then in the denominator is this. When I evaluate at b, I get b plus 3, and then we subtract off, but minus and minus is plus, and then I evaluate at the lower limit of integration. I have 6 over 1 plus 3, which is 4. This was fundamental theorem of calculus. Now I'm ready to take this limit as b goes to infinity, grows without bound. And it's here. What's happening here? Well, b is growing without bound. Minus 6 over b plus 3 is going to 0. This limit is 0, and we can see our answer. It's 3 over 2. This improper integral converges, and it converges to 3 over 2. 1b. Well, if we look at this example, we have to be a little bit careful because it looks like a definite integral, but it is not, because here, the denominator is 0 at 28. So this is improper, and it is a type 2 improper integral. The first part is to write the definition. This is a limit as b approaches 28. Technically, as I mentioned in class, it's a limit on the left, and then we have an integral from 1 to b. Just like in the example above, I'll write this as a power. It's x minus 28 to the minus 1/3 power. Okay, and also just like the example above, my inside function has derivative 1, or if I were to write out the steps of substitution, du would be dx. I'll just integrate, just like I did in 1a. So this is a limit as b goes to 28 on the left. And then we add a power and divide by the higher power. This would be x minus 28 to the 2/3 power divided by 2/3. And we evaluate between 1 and b. So I keep writing limit until the very end when I actually evaluate the limit. Well, my coefficient here is 3 over 2. And then I have b minus 28 to the 2/3. And then subtract off, evaluating at the lower limit of integration. I will have 1 minus 28, which is negative 27 to the 2/3. Now, I'm done with the definite integral part, and I just need to evaluate this limit. So it's here. Well, this function here, this part, this is continuous at 28. And so I just evaluate. 28 minus 28 is 0. So this part approaches 0. And this is another convergent improper integral. Now, the thing is, I have to be careful about the sign. So let's think about this part. There's a few ways I can do this, but probably easier is take the cube root and then square. The cube root of minus 27 is minus 3. We square, we get positive 9. Positive 9. And then multiply by 3. So this part is positive 27 over 2. But then you see I have this subtracting off. The whole thing is negative. So my answer is negative 27 over 2. And once again, we have a convergent improper integral in 1b. 1c. This is actually a really fun problem. Without the hint, I think it would be too tricky as what do you even do? Because without the hint, you just look at this and then you're like, I have no idea how to integrate this function here. But with the hint, this problem is very fun. In fact, I found this on a final from several years ago for this course. But you see, with the hint, it makes it reasonable because we see an inside function. And look, we have multiple of its derivative in the integrand. This is when you know to use substitution, when you see an inside function and a multiple of its derivative in the integrand. So this is substitution. But before I do the substitution, let's start by writing the definition. This is a limit. As b goes to infinity, the integral from 0 to b, and then of this, e to the x divided by, I'll even include my hint here. This is 1 plus e to the x squared dx. Okay, so now you see inside function, multiple of its derivative, in fact, its derivative, exactly, the multiple is 1 in the integrand. So let's write out the work for substitution. U is e to the x, du, e to the x, dx. Okay, and we have exactly du in our integrand. Now, me personally, I always convert my limits of integration to u limits. My x's range from 0 to b, and u would be e to the 0, which is 1. And here u would be e to the b, which is just how I will leave it. So I have a limit as b goes to infinity. And it's important to understand this part did not change. I'm doing substitution on the definite integral. And at the very end, I will take a limit. We have an integral from 1 to e to the b of 1 over 1 plus u squared and du. This is the tan inverse here. An antiderivative for 1 over 1 plus u squared is tan inverse of u. This is the next step. This would be a limit. As b goes to infinity, just like I said, we have tan inverse of u. And then we evaluate between 1 and e to the b. And this becomes what we see here, a limit as b approaches infinity, tan inverse of e to the b minus tan inverse of 1. Well, how do we address something like this? First of all, we have to evaluate tan inverse of 1, and then we have to think about the tan inverse of e to the b as b grows without bound. So tan inverse of 1, maybe I will draw a unit circle over here just to think about this. Here's my unit circle. This says the tangent is 1. Say tan theta is 1. Theta is what? Well, I need to put the restrictions of it being the tan inverse function, right? It needs to fall between minus pi over 2 and pi over 2 here. So I'm looking for the angle between minus pi over 2 and pi over 2 such that the tangent is 1. tangent, sine over cosine, and the tangent is 1 when they are equal. So we're looking for right here where sine and cosine are the same. This happens at pi over 4. Okay, so here. So this helps us with this part. Tan inverse of 1 is pi over 4. Maybe I'll go ahead and write that part. This would be over here. Now the question is about this, the limit. Well, inside, okay, this part, this is going to infinity. And so the real question is, what happens to, say, tan inverse of, say, x as x grows without bound? Or the limit as x goes to infinity of tan inverse of x? That's really what I'm asking here. So hopefully you know this. If not, let me include a picture we can see of the graph. Hopefully you can see this in the video. I can add these, should go this way and this way. So this is a graph of the tan inverse. And hopefully you can read this and you can read this. But it sits between minus pi over 2 and pi over 2. And here the limit as x goes to infinity of tan inverse x is pi over 2. Similarly, the limit of tan inverse of x as x approaches minus infinity is minus pi over 2. But I'm interested in positive infinity here. So this one is pi over 2. Maybe I should circle that. This approaches pi over 2. This is another convergent improper integral. So we have pi over 2 minus pi over 4. And our answer here is pi over 4. Okay. This is a fun problem. This was 1C. This is our last improper integral on the quiz practice. And once again, if you look at it too fast, you might think it's a definite integral, but it is not. Because if we look at the denominator, this denominator is 0. Well, 0 at 3 and minus 3, but in our interval, it's only here at 3. So this would be a limit as b approaches 3, is coming from the right this time. And then we have an integral from b to 5. I'm going to go ahead and write the denominator part as a power, right? We have a square root of something cubed. The power here is 3/2. We have x squared minus 9 to the 3/2, and then dx. Okay. One question that came up in class is, what letter does it matter? Because you could use A. I used B. You could use T. Okay, it's just a letter. So you could, doesn't have to be a B. Just don't use an X because that's my variable in the question. But you can use a different letter here and it's really not a problem. So if we look at this function here, this is without a doubt substitution because we see an inside function and we see a multiple of its derivative in the integrand. So let us write the work. Just like the last problem, we'll write the steps for substitution. U is x squared minus 9, and then du 2x dx. Now we have x dx handed to us. It's here in our integral. And this is 1/2 du. And just like in the last problem, I personally always change my limits of integration. My x's range from b to 5, and here u will be b squared minus 9, and here u will be 5 squared minus 9, which is 16. Okay, so here's my work for substitution. And now I'll just continue the problem over here. This is a limit. As b goes to 3 on the right, we have an integral. Well, my limits have changed. It goes from b squared minus 9 to 16. These are u limits of integration. And then I have u to the minus 3 over 2 times 1/2 du. Well, I'm ready to integrate. We have a limit as b goes to 3, and I can add a power. divide by the higher power. We have a 1/2. That's the coefficient here. And then when we add a power, I get u to the minus 1/2. Divide by the higher power. We're dividing by minus 1/2. Maybe I will do this so it makes it a little more clear. And then evaluated between our two u limits of integration. You see, I have not evaluated a limit yet. I am still in the definite integral part of this problem. Here, what's my coefficient? Well, we have a 1/2, and then we would have a -2 in the numerator, so it's just -1. And then this is a square root in the denominator. I will put it in the denominator just because it helps me when I get ready to take a limit. At my upper limit of integration, it's here. And then subtract minus a minus, this will be a plus. And I have here square root b squared minus 9. And b is approaching 3 from the right. Well, this part is just -1/4, but here, the denominator is going to 0. And so this fraction is going to infinity. But this is going to infinity. And so this limit does not exist. We conclude the improper integral diverges. This is the language. The first three, A, B, and C, they all converge because the limit existed as a finite number. Here, this improper integral diverges. Now we move on to two numerical integration problems. The first one is Simpson's rule with n equals 6, and we want to approximate this definite integral, the integral from 3 to 15 of x over ln x dx. So the steps here, the first thing we do is we calculate delta x, which is always b minus a divided by n. And here, this is 12 over 6, which is 2. Then, after we have delta x, we write down our partition. So we start with the lower limit of integration, and we march forward by delta x until we hit the upper limit of integration. So this would be 3, 5, 7, 9, 11, 13, and 15. And we should have 6 subintervals here. We can check. We have 1, 2, 3, 4, 5, and 6. We will always have one more element in the partition than we have subintervals because, well, the indices went from 0 to n. So there's n plus 1 elements in the partition using the given n. Here we have 6 and 7. Very nice. Okay, that was step 1 and 2. Next, the formula for Simpson's rule. This one has a delta x over 3. And then we take f of the first, where the integrand is f of x. Okay, then it goes 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, like this, until the very last one has coefficient 1. So we would have 4 f of 5 plus 2 f of 7 plus 4 f of 9 plus 2 f of 11 plus 4 f of 13. And then the very last one comes with coefficient 1. So this will just be f of 15. Just like this. And I will highlight here, this is what makes it Simpson's rule is 4, 2, 4, 2, and 4. Well, together with delta x over 3. Maybe I should highlight that too. If we had trapezoid here, this would be delta x over 2, and this would be 2's. And that's the main difference in the formulas. Of course, where they came from is different too. Trapezoid rule uses line segments to approximate the integrand, and Simpson's rule uses quadratic pieces. But in terms of a formula, they're just slightly different looking. This is Simpson's rule. Now, let us take one more step. This would be 2 over 3. And then we would have 3 over natural log 3. plus 4 times 5 over ln 5 plus 2 times 7 over ln 7 plus 4 times 9 over ln 9 plus 2 times 11 divided by ln 11. And then we have a 4 times 13 over ln 13. And finally, just 15, 1 times 15 over natural log 15. Okay, typically, and read the directions on your quiz, but typically we would round to say 4 decimal places. But one thing I mentioned in this class, you do not want to start rounding each one of these separately and then add them all up and round, because that will cause rounding errors. What you want to do is enter this entire line into your calculator. So let me show you, for example, here. Okay, this is where I entered it into Desmos, but you can see I entered the whole line into my calculator, which was Desmos. And you can see here is what I get back. So the answer rounded to 4 decimal places, I would just copy it, would be 49.1489. Number 3, we will use the trapezoid rule with n equals 4 to approximate this integral. I really like this one. This one came off a midterm of mine, maybe last year sometime, because so much of it we can do by hand, as we will see. So the first step, just in the last, like in the last problem, is calculate delta x, which is b minus a over n. And the next step, after we have delta x, pi over 2, we write down the partition. Okay, start at the lower limit of integration and march forward until you hit the upper limit of integration. We have pi over 2, pi, 3 pi over 2, and 2 pi. And just like I was talking about in the last problem, just check. We have 1, 2, 3, 4 subintervals. Very nice. Now, trapezoid rule has a delta x over 2. And then we have f of 0. But all the middle ones have coefficient 2. So we will have 2 f of pi over 2, 2 f of pi. We have 2 f of 3 pi over 2. And then the last one has coefficient 1, so f of 2 pi. Okay, maybe I'll highlight it just like before. What makes the trapezoid rule in terms of a formula is the pi over 2 on the outside, and then all the 2's on the inside. Coefficient 1, coefficient 1. Okay, that happens in both formulas, in fact. So now let's do this. Delta x is pi over 2. So out here is pi over 4. And then, well, f of 0 is 3 to the sine 0. Maybe I'll take this step and write this with the signs, and then I will actually evaluate all of this. Then we have 2 times 3 to the sine pi over 2. And then 2 times 3 to the sine of pi. We have 2 times 3 to the sine of 3 pi over 2. And finally, we have 3 to the sine of 2 pi. Now, just like I was saying when I started this problem, we can do this by hand. We can evaluate the sign at all of these values. The sine of 0 is 0, and so 3 to the 0 is 1. The sine of pi over 2 is 1, so we have 2 times 3. The sine of pi is 0, so we have 2 times 1. The sine of 3 pi over 2 is negative 1, so here we have 2 over 3. And finally, the sine of 2 pi is 0. So again, we just have 1. Now, you see, this is what I was saying, how beautiful this is. We can do this by hand. This is 6, 7, 8, 9, 10, and 2/3. which is 32/3. And this simplifies to 8 pi over 3. Now, to get to round to 4 decimal places, that I couldn't do by hand. Let's see what this is. I have it in my calculator. 8 pi over 3, this is approximately 8.377, and then it goes 5/8. So I will do 6, and this is to 4 places. And this completes this problem using the trapezoid rule to approximate this definite integral. This has been extra practice for quiz 2. Thank you all so much, and good luck on the quiz this week.